This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Thank you, Harry. Our second speaker will be Mario Molina, who won the Nobel Prize in Chemistry in 1995 for his work in atmospheric chemistry, particularly concerning the formulation and decomposition of ozone. Mario grew up and attended elementary and high school in Mexico City. He got hooked on science while in elementary school when he first looked at paramecia and amoebae through a toy microscope. This led him to convert a home bathroom into a laboratory where he spent hours playing with chemistry sets. By the time he was 11 years old, he had decided to forego pursuing a career as a violinist in favor of becoming a research chemist. That's foresight. After high school, Mario earned his bachelor's degree in chemical engineering at UNAM, the Autonomous National University of Mexico. He then studied at the University of Freiburg in Germany, for 2 years before returning to UNAM, where he started its graduate program in chemical engineering. Realizing that he needed to pursue his education further, Mario enrolled in Berkeley's physical chemistry program, where he earned his PhD in 1972. He then went on to UC Irvine as a postdoc to work with Sherry Rowland, with whom he would share the Nobel Prize in 1995. Their work shed important light on the impact on the ozone layer resulting from the release of chlorofluorocarbons into the atmosphere. Mario was appointed to the faculty at Irvine in 1975, but in 1982, he moved to the Jet Propulsion Lab at Caltech so that he could spend more time conducting experiments with his own hands. While at JPL, his work contributed substantially to our understanding of the loss of the ozone over the South Pole. In 1989, Mario moved to MIT, where he continued to work on atmospheric chemistry. Fortunately for us, in 2004, Mario came to UCSD to join our Department of Chemistry and Biochemistry and the Scripps Institution of Oceanography, and he continues to work on air quality and climate change issues. At the time he moved to UCSD, he also established the Mario Molina Center for Strategic Studies in Energy and Environment in Mexico City, which has a primary focus on addressing the problem of air pollution and improving air quality. So please join me in welcoming Mario Molina.
Thank you very much. I'm very pleased to be here and to have the opportunity to talk to you for, it's supposed to be 20 minutes. I'm going to try to stick to that. And for a moment, I thought I was going to have a very challenging time talking about science with an economics PowerPoint, but fortunately, I think I recovered that. Well, I'm going to just to try to tell you about the research that led to the Nobel Prize, but I'm going to start going back in time a bit further. I wasn't born at the time that this slide represents. It was born a little later, so this is about 100 years ago. What happened then? Well, something very interesting happened with refrigerators just about 100 years ago, namely that these electrical machines were developed. Before that, people used to have freezers or refrigerators at home, but they worked with big chunks of ice. I know in Boston and in New York and so on, there were some big business importing frozen chunks of ice from frozen lakes. And I wonder what was the situation here in San Diego. But it must have been hard to have these machines. But anyhow, this was very nice that electrical appliances came to being. However, these early refrigerators did have a problem, and it was the following. Occasionally they failed and they leaked. And so there were a few bad accidents. In fact, some people actually died because the refrigerant that was make these refrigerators work was something like sulfur dioxide or ammonia. These are poisonous gases. Okay, so something had to be done, and fortunately, chemists helped to solve this problem, and they developed what for many years was understood to be miracle chemicals. Okay? They have this long name, chlorofluorocarbons, but CFCs for short. These are industrial chemicals. They do not exist naturally. But essentially what they do is replace these poisonous refrigerants. These are compounds. The main property that makes them useful for refrigerants is that you can convert them readily from liquids to gases at the appropriate temperatures. That's the first property. And the second property is that they are very inert. You can breathe them and usually don't get poisoned. Because of that, these miracle chemicals, of course, were a big success, not only with refrigeration, but they also began to be used as propellants for spray cans. And spray cans became very popular again in the first half of the century. So at some point in time, I remember statistics that a typical household in the United States had something like 30 or 40 different cans, spraying everything from toothpaste to underarm deodorant to what have you. But the point is that you're going to breathe the propellant, which is, the idea is to have a compound that under a little bit of pressure is a liquid, so you can have a lot of it in the can, and when you press the valve, the liquid evaporates and carries with it the deodorant or whatever you need. So that's where our story really begins. There's one more point here that to mention is that these compounds being so stable, they were, because of their use, they were just being released to the atmosphere. So it became possible to measure these compounds. And so this is a graph here of a set of measurements by a good colleague of ours who developed a machine that was able to measure very small amounts of these compounds. And he found them, as expected, not only in the northern hemisphere, but also in the southern hemisphere. Very small amounts. So it's at this stage that, together with my colleague Sherry Rowland, when I finished my PhD at Berkeley in very fundamental chemistry, I decided with Sherry to do something applied to use. He was also not an atmospheric chemist or environmental chemist, but we both decided to see whether we could sort of apply our knowledge to something closer to the societal problem. And we decided we would learn about the atmosphere by choosing a problem. If we could solve a problem connected to chemistry and to the atmosphere, that would be a good way to learn about it. And the problem that we chose was fairly simple. What happens to these compounds that were piling up? Is there anything to worry about, or will they pile up indefinitely? At that time, we didn't know that actually several other research groups had asked the same question, and they concluded essentially that nothing would happen. We came to a different conclusion. And to explain what the conclusion is, just to explain very briefly the most important property that describes the different layers of the atmosphere is temperature. It's graphed here, but I can merely explain it. As you know, temperature drops as you go to higher altitudes. We certainly know as you go to mountains and so on. It gets cooler and cooler because of the fundamental physics that the air parcel, as it rises, it expands and cools and so on. But this cooling doesn't continue indefinitely. At some stage, the atmosphere begins to warm up, so temperature starts to increase. And that's what defines the second layer. The bottom layer is called the troposphere, the next layer is called the stratosphere, and that's a layer where temperature no longer decreases. It increases, and because of these profiles, they're sort of separated. They don't mix with each other very, very rapidly. Well, that's all we need to know to address this problem. What we found, what appeared to be a little boring at the beginning, is that these compounds, the CFCs, piling up in the lower atmosphere, were indeed so stable that nothing would happen to them at these low altitudes. Normally, species emitted by pollutants or natural or so, most of them are removed, for example, by rain if they're water soluble, or they get oxidized, they suffer some chemical reactions, and they get removed in the lower atmosphere. But these species, because they were designed to be very stable, they actually survive, penetrate into the second layer, the stratosphere. Now, what happens is the reason that temperature increases at those altitudes is because there is a certain compound at those altitudes that absorbs energy from the sun. And this compound is ozone. Okay. It's not very abundant. It exists even where it's most abundant, only at parts per million level. But actually, life evolved in the presence of this ozone layer that exists in the stratosphere, because otherwise radiation from the sun would have destroyed molecules for life, like DNA and so on. So we have a natural protection that allowed life to evolve and so on, which is the reason why you have this inverted temperature profile up there. Well, what happens then, with all this background, I can summarize then what our finding was in relatively simple terms. Again, to repeat it, these compounds release at the surface, they mix rapidly in the lower atmosphere. It takes them much longer to reach the stratosphere, at least a decade or two, but eventually in the stratosphere they move to the middle or above the ozone layer. And then they find this radiation from the sun that fortunately doesn't reach the surface, the one I was alluding to that destroys biological molecule. Well, that radiation also destroys the CFCs. So that's what happens to them. That's where they end up being destroyed at these high altitudes. So that answered the question that we posed, but we didn't quite stop there. We say, well, so what? Is there any consequence of these chemicals getting to that altitude? And what we realized, being chemists and so on, is that ozone, being a very unstable molecule, that the decomposition products from the CFCs would actually destroy ozone very efficiently. And that's what I have just summarized here. Through a mechanism called catalytic cycles, that means that very small amounts of these decomposition products can destroy large amounts of ozone. This is as much chemistry as I'm going to talk about, but this is just to put an example. The point is to explain how a catalyst works. In this case, chlorine atoms are the species that we worry about, decomposition products from the CFCs. They are free radicals. That means they are very reactive. You know about free radicals in your body that can do some harm and so on. These are molecules that just are chemically very reactive because they have an odd number of electrons. Well, they react extremely fast with ozone, but in such a way that the chlorine atom destroys an ozone molecule, makes chlorine oxide, and then the chlorine oxide reacts in such a way that you regenerate the chlorine atom. So you can go around and around, and that's why a single chlorine atom can destroy tens of thousands of ozone molecules. And that's when we realized, wow, we have this relatively small amount of chemicals released to the environment because the atmosphere is big. And so it's not that big. It's really like the skin of an apple, if you look at it from a global perspective. So from a planetary perspective, the atmosphere is very thin. But from the perspective of human activities, you're up 10, 15 kilometers above the Earth's surface. Not that far, okay? Just think 10 or 15 kilometers horizontally, you don't go very far, but if you go upwards, it's above where airplanes fly and so on. Anyhow, it's at those altitudes that with this amplification mechanism, we realized that we had a potential problem. It was just a hypothesis. It was in the 1970s when we postulated it, but that remained to be tested. But if the hypothesis were to be correct, then we would be in trouble because the ozone layer is so important to protect life on the surface. Specifically, for example, on people, it's the main cause of skin cancer, okay? Because this is what you get sunburns because of this radiation that is not perfectly shielded by the ozone layer. So if you affect it, you get more of that radiation. Okay, so that was the hypothesis. And then what I'm going to do is just to jump ahead. This was in the 70s, but it took about a decade or almost 2 decades working with the scientific community to really test the hypothesis. And when we first postulated it, we were talking about affecting the ozone layer more or less at all latitudes, not very specifically. But what eventually happened is we know that a very spectacular event started to happen over the Antarctic continent, namely what we now label as the ozone hole. And it started to develop in the 1980s, okay? And so ozone drops very fast in the spring months, which is in the southern hemisphere, September, October, and so on. And to explain, perhaps in clear terms, what happens in this figure, by the way, I'm using sort of historical copies of view graphs that I used to use many, many years ago, so that's why they are sort of hand-painted. But what we have here is a typical ozone profile. That's the blue line, which represents that there's a maximum amount of ozone in the ozone layer in the stratosphere, about 15 kilometers sort of in the, over the South Pole. And in the spring term, in the spring months, when the light begins to show up over Antarctica after the long winter, where it's dark for several months, you have this very spectacular phenomenon where ozone begins to disappear very fast. So at the altitudes where it's normally most abundant, it practically all disappears, more than 99% goes away. So when it was first found, and the scientific community thought, well, maybe it's such a big event, it must be natural and so on. But of course, we were able to show that with laboratory studies and so on, that in the presence of ice clouds that exist at those altitudes, that really this was a consequence of the presence of these free radicals coming from the CFCs. And so there, as an example of how the science got really pinned down, there were actually some measurements carried out over Antarctica. This is ER2, which is the same plane as the U-2, the spy plane. Some of you might remember that one of them got shot down over Russia and so on. So it was really developed to spy when we had the Cold War. But fortunately, later on, it could be converted to do more scientific research, spying as to what was the chemistry of the stratosphere. And so some experiments were designed to find out what the ozone hole was all about. So this is, again, a little bit of a historical graph, measurements by my colleague Jim Anderson from Harvard, which show in the upper graph what was happening to ozone as the aircraft penetrated into this polar vortex, which is where this event happens. And early, when the light was just beginning to appear, ozone was very stable, not much was happening, but it was already possible to measure that practically all the CFCs that were there originally had been converted to this free radical form in the presence of these ice clouds. And in just a matter of weeks or so, it was quite spectacular to see this anti-correlation. As you penetrated the ozone hole, it's clear that to the extent that ozone was going away, you had this amount of the free radicals, and again, it was not hard to show that with this mechanism, you could explain how most of it was actually going away. So in some sense, this was like a smoking gun. There's a big ozone hole over Antarctica, and it's the science showed very clearly that it was a consequence of the presence of these CFCs. Of course, at other, I won't dwell on this, but other latitudes, ozone was disappearing as well. It was just not so clear, not so spectacular a phenomenon. I need to finish now, but let me just show a couple of more slides. What this led to, this was the basic science, this led to an international agreement, working together with the international community. Fortunately, essentially all the countries of the planet, more than 190 or so, agreed that these compounds just could not longer be manufactured. So there was a ban on the production of these compounds precisely to protect the ozone layer because of the consequence we talked about. The first part was in the 1980s, and so the measurements that were showing up that these species were piling up, when industry realized that the science was so strong, then they started to reduce the emissions, and so the measurements showed that very clearly. But here is another way to look at it. With no controls, the emissions were going up very rapidly. The first version of this international agreement, the Montreal Protocol, was relatively weak, but it got successively strengthened so that with the Copenhagen Accord, the agreement was that in 1996, these compounds would no longer be manufactured except small amounts in developing countries. And so here is what we have now. The observed amounts of ozone, of course, as an average, have indeed decreased, and it will take some time for the ozone layer to recover because these compounds remain in the atmosphere for about a century or so. So we expect the ozone hole to recover only sort of mid-century now, because that's how long these compounds stay there. However, if we had not been successful with this international agreement, then we would have expected the ozone layer to really be depleted, and we would have very big trouble, not just in terms of ultraviolet radiation, but really changing how the atmosphere functions. So let me just very briefly just mention that there are some important lessons, but I'm a little bit after time, so I won't dwell on this. The important point here is that we have other environmental global problems like climate change and several others, but we have at least this one example of something that actually worked, where the countries of the planet actually did agree to do something about it, and where the problem has been essentially solved. Early on, spray cans, of course, was part of the solution. They continue to be used, but they used other propellants like hydrocarbons, no longer CFCs, and for other uses, such as to clean electronic boards. At some point in time, people thought this would be practically impossible without CFCs, but of course, the technology was developed to replace them. So let me just end with this to show another perspective of the atmosphere. It's indeed very thin, very fragile. We know that with 6.5 billion people that we have on the planet, we are doing all sorts of things to the natural resources of the planet, but the atmosphere is one of those resources. But I hope we can learn from this successful example that people can actually agree and solve problems. And it turns out that even though initially there were some worries about whether it would cost a lot to solve the problem, the cost was really minimal. Society barely noticed, and the problem was solved, and standards of living continue to rise everywhere. And developing countries, of course, have now refrigerants, spray cans, and so on, but they were able to avoid these species. So anyhow, this is, in a nutshell, the research that led to the Nobel Prize. Thank you for your attention.